Okay, so we should be live with another assumptions of physics session of the reading group, and we'll wait a second to see if there is somebody else joining. And in the meantime, so last time we talked about something completely different, so there is really no need to do a recap, which was why there are three dimensions, and today instead we'll be looking at why essentially. So we already know why we have the structure of phase space, and now we are going to discuss why essentially do you have the structure of the manifold, I think, before the phase space. So that basically tells you why do you have all the pieces of classical mechanics. So as usual, I'll share my screen. There we go. And I've put the link in the chat for people that want to follow there. And why don't we start, Julius?
All right. So infinitesimal reducibility. We have seen that the structure of phase space, the symplectic structure, is exactly the structure needed to describe density, count of states, and entropy in a coordinate invariant way. This simplicity assumes that states are points on a differentiable manifold. That is, they are fully identified by real variables that only allow differentiable changes of variables. We will see that this corresponds to the assumption of infinitesimal reducibility. Should I continue?
Sure.
I can. Particles as infinitesimal parts. At this point, we have ample evidence that the correct fundamental object that describes classical systems is not a point on phase space. All physical objects have finite spatial extent, and assuming otherwise leads to problems. A finite mass concentrated at a point is incompatible with general relativity, as it would puncture spacetime and not travel along geodesics, and with quantum mechanics, as it would imply uniform spread in momentum, thus requiring infinite kinetic energy. The correct physical object, instead, is a distribution over phase space. It explains the very structure of phase space. The distribution has to be frame invariant. It explains why the laws of motion are differentiable. They transport a density, not just points, and why they follow Hamiltonian mechanics for isolated, deterministic, and reversible systems. We can therefore conclude that the state of a classical system is given by a distribution over a phase space.
Yeah, you can finish the paragraph.
Okay. As usual, in reverse physics, we want to find equivalent physical assumptions for the same statement.
Okay, so let's see. The mathematics would mean that all mass energy would be concentrated in points of infinite curvature, leaving the rest of space-time flat with no mass. So this is the problem of a mass concentrated in a point in GR. And then in quantum mechanics, mathematically, the wave function will be a delta function, which is not even an element of the Hilbert space elsewhere. So that's basically why point particles are problematic in all of physics, and so we should also consider them problematic in classical mechanics. Ben.
All right. While point particles should not be considered fundamental classical objects, the whole of classical mechanics assumes them and uses them. Therefore, we should understand exactly what they represent. One way to understand point particles is as an approximation. When we calculate the trajectory of the Earth around the Sun, the motion of a cannonball, or the average displacement of a molecule under Brownian motion, we know that the object is not actually point-like. But since the body is rigid, and assuming that the effect of external forces on the different parts of the body can be neglected, we can get away with studying the motion of the center of mass. Clearly, we need to check that the assumptions hold, or that the assumption holds during the whole motion. If the distance between a comet and the sun becomes smaller than the radius of the sun cannot be assumed to be point-like anymore. The approximation will also fail if the force exerted on different parts of a body is greater than the force that keeps it together. The point particle approximation is not unique to classical mechanics. Quantum mechanics, through the Ehrenfest theorem, also allows for a point particle approximation, which will fail if the wave function is spread over a region where the potential changes are non-negligible. Since the approximation is not unique to classical physics, the characterization of a point particle does not help us understand the fundamental constitutive assumptions of classical mechanics. When discussing the nature of Hamiltonian evolution, however, we saw that states were better understood as infinitesimal regions of phase space. This means that classical particles, at least this more fundamental version of them, can't be understood as a standalone physical object. They should really be thought of as the limit of some recursive subdivision. That is, classical particles should really be thought of as an infinitesimal part of something bigger, and the part in particle should be understood literally. The actual classical object, then, is not the infinitesimal part, but the whole object that can be, in principle, divided into infinitesimal parts. In the same way that, when discussing differential topology, we had quantities over finite regions that could be broken into the infinitesimal contributions, the whole object, together with its notion of state, can be understood as made up of infinitesimal parts. So the classical system can be thought of as being made of infinitesimal parts called particles, right? All classical systems follow the assumption, not just mechanical systems. Continuum mechanics and fluid dynamics assume that the materials are a continuum of infinitesimally small parts. Classical electromagnetism assumes that electromagnetic radiation can be decomposed into arbitrarily small signals at all frequencies. Moreover, the assumption clearly fails in quantum mechanics. In that case, we cannot talk about the state of a part of an electron. Materials are not a continuum of infinitesimally small parts. The intensity of the electromagnetic radiation cannot be made arbitrarily small.
Okay. Make sense?
Yeah, I guess we need to see this in realization when we consider some basic interactions. Because, for example, center of mass is applicable when I know, let's say in classical physics, it's not such a big problem, but in nonlinear physics, then it's more difficult to define. So I guess some additional assumption will be required to allow treating center of mass as a point particle.
Yeah, in fact, I also. So one of the things that I'm still sort of, let's say, I don't know exactly how to actually work properly. So for defining a central mass, you are basically taking an average. And you do the average on the coordinates, right? You take the value of the coordinates, you take a distribution, you do the average. If you do a nonlinear transformation, that center of mass is going to be different. So if you have sort of coordinate systems that are, so if you assume that locally you have an inertial frame, and then you define the center of masses on inertial frames, then it's fine. Like locally you can define a center of mass if things are small and so on. If it's too big, or you are in general relativity, right, that yes, you can do it locally, but then you extend your distribution for a little bit, you can't do it anymore. And there are similar things that happen in quantum mechanics as well, because when you do the operators, you do expectation, you're doing, and so there is something there that it's a link between statistics and being able, and sort of inertiality, that it's something that I think needs to be really properly thought out, and it's one of the yeah, it's one of those things that I haven't fully fleshed out. But if you can assume that you have parts and you divide everything into parts, at least you can say that you have the distribution. Then whether you can take the center of mass, it's a secondary problem. At least you have the distribution, and then you can change the distribution in the nonlinear frame, and so at least the center of mass changes in quotes, but at least you know what you're talking about. But yeah, so I'm aware there are all these problems. They're not here because we're just trying to understand what happens with distributions. But yeah, it's one of those things that sort of get swept under the rug in physics, or most people don't even think about the details. So.
Yes, yes. I believe that at least for center of mass, although we talk about it in very intuitive manner, but if one digs deep enough, I think you can find that these are all theorems, and theorems depend on assumptions, and it's not that center of mass is always fundamental or can always replace the object. Even in classical physics, let's say as soon as we are dealing with nonlinear forces, then okay, center of mass drastically it changes its meaning. Let's say one compared just to, let's say, what is a momentum, center of momentum, something like that. So
yeah, so
yes.
this goes in basically coincide with what we were saying, that the point particle with center of mass is an approximation, and then you can use it if you are in the realm of possibilities where those approximation holds. Okay, let's
Okay.
continue.
Yes.
Before
Divisible.
Oh, Ben has a question. Go ahead.
Yeah.
correct me if I'm wrong, but it seems like mathematically we're talking about a kind of redundancy. Like, say you take the Earth-Sun system, right, and you want to kind of like reduce it to just like the information about the centers of masses and their velocities. Um, in some sense, like this is a good approximation if you can take your original phase space, which is very large, and like map it onto this much smaller phase space that contains basically just 4 coordinates. And then if the induced time evolution is still 1-to-1, like just knowing the centers of masses and their velocities of the original system tells you what the center of mass and velocities of the system will be at a later time, at least to a good enough approximation, then the approximation that you've made is in some sense physical, right? Um, so and then for instance, if you have like the planet passes in like too close to the Roche limit and it splits in half, and suddenly the center of mass doesn't represent the center of an actual object, then it's going to start doing like weird behavior that you wouldn't have been able to predict just from knowing what the centers of mass are. And so then the like two initial conditions with the same centers of mass and velocities of the centers of mass would like take different paths as you evolve through time. So like in some sense, this is almost like you're taking like fibers of the time evolution and like identifying them.
Yeah, so basically, like in physically, you need to be sure that essentially the variable that you're studying truly decouples from everything else, right? That it's like so one way that I think about it, like the fact that you have the laws, the sort of deterministic laws, is because you have chosen the right variable that in that specific situation form a closed system. Like those variables are enough.
Mhm.
It's not a given. Like it's part of specifying the physics problem is to find which variables in particular circumstances sort of are enough for the process at hand. So if you're doing thermodynamics and you're doing pressure, volume, and temperature, right, and you're at equilibrium, oh, it's the same thing, like that's fine, right? But then suddenly, if you're doing something else, then the distribution of the molecule might actually be important because you need to study what you study. So what you're describing, it's a similar situation. You have a system where at the beginning, yes, the center of mass and the velocity of the center of mass is enough, but then something happens where now the internal structure was actually relevant. And I think this is what like we're trying to, like these type of things are exactly what the type of that we're trying of the type of assumption that trying to bring out through the program, and understanding exactly, for example, if I define a system, what is it that I'm doing? How do I know which variables to pick, which processes I'm limiting myself, right? So if I've picked out some variables, it means that I'm only going to study processes in which those variables are well defined, at least, and they're relevant, and I can describe the system through that process. So yeah, this is all, yeah.
Okay, shall we continue?
Yeah.
Okay, divisible versus reducible. Before going forward, we need to be clear as to what being made of actually means. For example, if we say that a table is made of horizontal top and 4 legs, we may mean that we can take the table apart and study its components independently, or that we can describe the whole table by describing the top and the legs. While often one can do both, these are actually different properties. That is, divisibility, the ability to cut an object into independent parts, is not the same as reducibility, the ability to describe an object in terms of parts. Let us go through some examples. Suppose we have a planarian worm and we divide it in half. After some time, the tail will regrow a head and the head will regrow a tail. We will be left with two worms. A planarian worm is divisible into two worms in the sense that we have a process by which a worm is divided into two worms, but it is not reducible to two worms, in the sense that describing one worm is not the same as describing two worms. Now, suppose we have a magnet. We can describe it by describing its north and south pole. Now, suppose we divide it in half. Each half will be a new magnet with its own north and south pole. A magnet is reducible to a north and south pole, meaning that describing a magnet is the same as describing its poles. But it is not divisible into a north and south pole, meaning that we do not have a process that can separate the two. We can also find differences between divisibility and reducibility with fundamental particles. Suppose we have a muon. If we wait some time, it will decay into an electron, a neutrino, and an antineutrino. A muon divides itself into the three particles, but it is not reducible to the three particles. The state of a muon is not equivalent to the state of an electron and two neutrinos. Suppose we have a proton that is not a fundamental particle, and it is described in terms of quarks and gluons. However, if we try to separate one of its quarks, the interaction energy will create new quark-antiquark pairs, and the proton will divide into multiple hadrons. A proton is reducible to quarks and gluons, but it is not divisible into them.
Okay, makes sense.
Yeah, I think so, yeah.
This is one of the things that it's kind of uh, almost indistinguishable in classical mechanics, but it's actually different, and it's one of the things where people get confused then in quantum mechanics. So Ben, would you like to continue?
Yes. Okay. Divisibility here means that we have a physical process that starts with the overall system and ends with the parts that can now be independently manipulated. Mathematically, if S sub C is the state space of the overall system and SA and SB are the state spaces of the parts, we have a time evolution map UT, which sends SC into SA cross SB that takes an initial state of the composite and returns a state for each part. This is not what we want. Reducibility means that describing the whole is the same as describing the parts. Mathematically, the state space of the whole system SC equals SA cross SB is exactly the Cartesian product of the parts. In other words, what we are talking about is not really the whole object, is not really the object itself, but its state. This is the type of partitioning we are going to use. To make reducibility more concrete and intuitive, suppose we have a ball. We can throw the ball and study the motion of the whole ball. We can also take a red marker, make a red dot on the ball, and study the motion of the red dot. We say the ball is reducible because studying the motion of the whole ball is equivalent to studying the motion of all possible red dots. It is infinitesimally reducible if we assume that we can make the red dot arbitrarily small. This is the property that we're interested in. Conversely, suppose we have an electron. We can study the motion of the electron, but we cannot make a red dot on the electron. We have no process at our disposal that can tag a part of an electron so that we can interact with and study only that part. Whenever we interact with the whole electron. This means that the assumption does not hold in that case. So condition This is the infinitesimal reducibility.
Yeah.
Then is a property of classical systems and only classical systems, and it is clear that irreducibility of the distribution implies infinitesimal irreducibility. But is the converse true? That is, if something can be thought of as being made of infinitesimal parts, does it follow that the state of those infinitesimal parts should be represented by points in a phase space? In other words, is the condition of infinitesimal reducibility enough to characterize classical systems?
Okay.
All right. Should I continue?
Julius, we
I
usually
can.
do one paragraph per person, but since we are so few of us, we can even take bigger chunks.
Mhm. Okay. Classical systems and infinitesimal reducibility. Suppose we have a system that satisfies condition. Yeah. Under this,
Infinitesimal reducibility.
yes. Under this premise, we have two state spaces, SC for the full system and SP for the infinitesimal parts, the particles. Each state for the full system must tell us exactly how much of the system is in each region of SP. That is, for each state S in SC, we have an associated real valued set function, f of u as a subset of
Is
0 to 1. It's
F
in.
applied to U is is a number between 0 and 1. Basically.
That for every region U in SP returns the fraction of the system in that region of particle state space.
Let's look
I
at
see
the
some, yes.
footnotes. Yeah.
So a set function is a function that takes sets as an argument. And technically, the region U must be a Borel set, as these are the regions that are associated with an experimental procedure. These details are established in the physical mathematics part of the book.
Detail.
Okay. Moreover, reducibility implies F to be additive, meaning that if U is the disjoint union of two regions, U1 and U2, then F of U equals F of U1 plus F of U2. Because we are assuming infinitesimal reducibility, this must hold not just in the finite case, but also in the countable case. Mathematically, F is a bounded measure. Since the state of the whole system is fully identified by the state of the parts, for each state S in SC, there is one and only one F. We can understand SC as the space of such functions. Yeah. Depending on whether we are considering a specific instance of a particular system or an ensemble of similarly prepared systems, the value of the function f will have a different physical meaning. It could be understood as the fraction of a single system that has a particular property. For example, half of the ball is to the right of the line, or it could be understood as the probability that a particular instance of an ensemble has a particular property. Half the time, the ball is to the right of the line. From now on, we will assume that we are talking about an actual system, but all that we say will apply to the ensemble case as well. Okay. The fact that f of u is a real valued, it is also implied by the condition of infinitesimal reducibility. Since the parts are infinitesimal and therefore there can't be a smallest increment. I'll maybe finish the paragraph or?
Yeah, okay.
Okay. It also implies that the fraction f of singleton, is it associated to a single particle state x of SP must be 0. Otherwise, we would be associating a finite non-zero fraction to an infinitesimal part x, which would make it not infinitesimal. The particle state variable SP of an infinitesimal reducible system then must be charted by continuous variables. Okay, so now we have a couple of footnotes.
Yeah.
Technically, this only limits the output of FU to be a bounded dense linear order. However, the function f must be closed under arbitrary countable addition, bringing in all the limits, meaning that the ordering must be complete. Lastly, the whole system can always be divided into countably many pieces, which tells us that the order must have a countable dense subset. Since the order is bounded, dense, complete, and has a countable dense subset, it is isomorphic to this interval, real interval of 0 to 1. And again, technically, we only found that the space must be in some sense dense. To show that it is dense like the reals, we need the link between topology and experimental verifiability that we establish in physical mathematics.
Yeah. For a switch reader?
Yes.
So far, we've found that under the condition of infinitesimal reducibility, the state space SC of a system is the space of all possible functions f of u in the interval from 0 to 1, where u as a subset of SP is a subset of all the possible particle states. Furthermore, the particle state space SP must be charted by continuous variables, and so it must be a manifold. We now need to recover the notion of differentiability and of invariance density. To be able to fully characterize the state of the whole system by the state of the parts, we need to be able to quantify the fraction of the system for each particle state. We saw that the fraction for each particle state is 0, which makes sense because particle states are limits. Therefore, the fraction associated to a particle state should be a limit as well. It should be a fraction density, similar to the mass or charge density at a point. Fraction density will quantify the fraction present over a region of particle states, meaning that it is expressed as a fraction over a count of particle states. We therefore need to be able to quantify how many states there are in each region of SP. We must be able to say which regions have equal number of states. Over a discrete space, this would be trivial. We could just count the number of points. But over the continuum, finite ranges have infinitely many points, and counting points doesn't work. We must have another set function, mu of u, which will also be countably additive, and as disjoint regions will identify entirely different states, making mu another measure. However, mu will be bounded only from below, i.e., no set can have fewer than 0 states, as SP can have potentially infinitely many possible states. Note that because of the infinitesimal reducibility assumption, we will be able to find smaller and smaller subsets of SP. The value of mu will keep decreasing, and in the limit of infinitesimal subdivision, we will have that mu of a singleton equals 0. That is, a single particle state counts as 0 in terms of number of states. In a way, the math is already telling us that particle states do not exist literally, and that the assumption of infinitesimal reducibility shouldn't be taken literally. It is a simplifying assumption and should be understood as such. In the same vein, as we can define distributions over phase space that have arbitrarily narrow spread, the entropy of those distributions can be an arbitrarily low number, which will tend to negative infinity in the limit of a delta distribution. This is clearly a problem, since thermodynamics requires the entropy to be non-negative. These two problems are in fact the same problem, since the entropy for a uniform distribution is the logarithm of the count of states. In other words, we shouldn't be surprised that classical mechanics fails for some objects, i.e. narrow distributions, or for ensembles with low entropy. It is exactly when the condition of infinitesimal reducibility fails. Continuing our derivation, we have seen that both the measure f for the fraction of the system and the measure mu for the count of the particle states are 0 for sets with single points. More in general, we must have that whenever mu of u is equal to 0, then f of u is equal to 0. That is, we cannot assign a finite fraction to a set of states that has no finite state count. That would, again, mean that we have a finite fraction associated to an infinitesimal subdivision, which is physically untenable. Mathematically, this means that f is absolutely continuous with respect to mu, and therefore we can define a density rho, which is d sub mu of f, such that f of u is equal to the integral over u of rho d mu. That is, the state of the whole system can be described by density over the particle states.
48. That rho is the Radon-Nikodym derivative. It's the measure theoretical way of defining derivatives. Okay, so we basically, the whole argument here is that we went from infinitesimal reducibility and we have found that we must have a density distribution over the states.
So as we said, SP is a manifold. The measure mu is a feature of that manifold in the sense that it depends only on the properties of the particle states, and it will be the same for all states of the whole system. Of all possible state variables that we can use to chart the manifold, then, it's convenient to choose those that can express mu as a density of states over units of the state variables. Mathematically, we are asking that the Lebesgue measure induced by the variable, say, this is like C, by the variable C, which maps SP into the real numbers, is absolutely continuous with respect to mu. This will also require that the variables are differentiable with respect to each other. It will lead to the differentiable structure. That is, insight 1.220, the differential structure of a state space is exactly the ability to express state count and fractions as densities over said states. Lastly,
So again, this was important to me because I want to understand where each mathematical structure comes from. And so the idea is that it comes from the fact that I want to be able to express densities. And if I can't, if I don't have variables that I can express density, I can't do other things.
Okay, yes. Lastly, both f and mu must not depend on the choice of state variables. Therefore, the proper expression of rho, which is the derivative of f, must also not depend on the choice of state variables. This plus assumption IND, I forget what that refers to.
Independence of the degrees of freedom.
Okay. Plus the assumption of independence of the degrees of freedom, as we've seen, requires the existence of the form omega and recovers phase space and the symplectic manifold. Therefore, we have recovered irreducible IR dist.
IR dist, exactly.
So condition IR dist is therefore equivalent to the condition of infinitesimal irreducibility. Classical mechanics describes exactly the systems that follow assumption IR, infinitesimal reducibility. The state of the system is reducible to the state of its infinitesimal parts. That is, specifying the state of the whole system is equivalent to specifying the state of its parts, which in turn is equivalent to specifying the state of its subparts, and so on. So assumption IR is therefore the constitutive assumption of classical mechanics. Assumptions IR, IND, and DR are the constitutive assumptions of the Hamiltonian formulation. Assumptions IR, IND, and KE are the constitutive assumptions of Newtonian mechanics. Assumptions IR, IND, DR, and KE are the constitutive assumptions of Lagrangian mechanics. We have found all the constitutive assumptions of all formulations of classical mechanics. We are now guaranteed that every result of classical mechanics is, one way or the other, explained by those assumptions. These are the only physical ideas that are strictly required to understand all the general aspects of classical mechanics. There is nothing else. Therefore, the goal of reverse physics for classical mechanics is reached.
Yay!
Sorry, I just have a question regarding
Yeah.
these assumptions. So I remember that in some of your talks, you talk about the problem of the lack of base theory to
Yes.
check importance of some of the assumptions. So now having this list, does it make your work easier, or you still need to do something?
Well, it gives me, so the goal of reverse physics is to find these starting points, and then the idea is to that inspire, like, gives you a direction to understand what you need for a base theory, right? So the fact that we have seen that the whole we have seen that even to define the state space, you need invariance of state counts, which means being able to define an entropy and all of those things, right? That means that the base theory must already have one way or another those elements. So it means that if in the base theory I don't have a notion of that it's equivalent to the notion of entropy, I'm not going to have enough information to characterize the physical theory, because the physical theory, because at least classical mechanics needs this, and doing the same things on quantum mechanics, it tells you also you need this. So it's like all the assumption points to what you need to construct the base theory, but these assumptions are all, and we know they're all optional, because we know that quantum mechanics will not follow the infinitesimal reducibility. We know that dr and ke are not required, because you can have classical theories that don't have that, right? So the base theory has to basically tell you all the things that you must have. So again, to do things properly, we would need a base theory, right? And then on top of that, we can say, oh, these assumptions are optional, and in these different cases, we get the different things. And the base theory is part of the part in physical mathematics, the part that we are building up.
Okay, and another question is to which extent we can just take what we considered so far, and we can just analogously apply this to field theories. Like, is there some obstacle that prohibits this these mappings or these requirements? Do we need anything like in addition to what we had in this, let's say, more like classical particle, solid object case?
So this is, I'd like to do it. We basically need to have everything that we said and just apply to field theory. We need a notion of count of configuration for fields, and a related notion of entropy for field configurations. So I need to be able to say, this is the space of all possible fields, this is a probability measure on that space, and then this is the entropy. If we were able to do that, we would probably go to Lagrangian field theory, understand what the Lagrangian density is, make similar thing that we did for the principle of stationary action for the Lagrangian. There is also a tight link between the Lagrangian formulation and the GR, in the sense that you take the Lagrangian and there are the sort of the massive parts and so on. So that might even allow us to understand better what the GR equations are doing, which is something that I still don't know. But first you would do it without, without curvature. And so those are the things that I'm actively looking for somebody to help me look, because I do not know how to do it. I quite frankly do not know. And the problem of putting measures on function spaces, it's one of those things where I kind of need to find the right person, because most mathematicians that I talk to, they don't have a sense that it's even possible. People that do stochastic processes instead, they say, oh yeah, we do it all the time, because that's what you do for stochastic processes. But for stochastic processes, it's like you have time and you're putting a sort of trajectory over time. So it's in a sense, it's simpler. For a field theory, you have sort of field configuration on both time and space, and the field configuration over space are where you are spreading your degrees of freedom. You're not spreading them in time. So there are all these issues that I do not know exactly how they're supposed to work. So how do you make, because we need to make the entropy invariant under coordinate transformations. So all these pieces, like I don't know how they fit.
Okay, and just a last question. I read that when one goes to, I don't know if it applies to classical field theories, but for quantum field theories, that you rather work with relative entropies, not absolute entropies. I know. Do you have you heard about this, and do you think like it's a problem that you only have information about relative entropy and not like absolute entropy for some system?
I've seen absolute entropy for field theory. So in a sense, entropy in quantum field theory is a little bit easier than in classical because whenever you have a pure state, you know that the entropy is zero.
Mm.
And in field theories, you can still you have different level of excitations and so on. So you can, as long as you have let's say finite subspaces, for example, right? It's clear what the entropy is. Like if you have a finite subspace and you have a uniform distribution over that subspace, you have that. Like it's not a, and even when you are in principle in using Fock spaces and so on, you are still separable. So any density operator that you might have can still be decomposed into a countable basis. Therefore, you get your eigenstate being the probability distribution, the probability values, and you can just calculate the Shannon entropy of that. Now, the fact that in principle you can do it, it doesn't mean that it's easy, comfortable, that you can do the things. And there might be lots of other problems because there are problems of infinity in quantum field theory because probably we don't have the right space. But at least there are some parts that I can that sort of are the same in quantum mechanics and quantum field theory. For the classical parts, instead, that there is no such thing. That the things have to be completely different. Because you basically need to talk about densities of degrees of freedom, and I don't know how to do that.
Okay, I see. Lots of challenges await us.
Yes,
Okay.
but it's one of those things where I feel that if you find kind of the right two or three person, one in probability theory, one in field theory, and so on, then you say, oh, actually, that thing connects to that, and
Mhm.
because I can't imagine that pieces of this type of math haven't already been built for something.
I mean, I have read something about these Gaussian measures or like free particle measures, and these are fine. These are
Mm.
giving the results as desired. But in general case, yes, I'm not sure.
So there are things called cylinder measures that I know that
Mm-hmm.
people use, but I don't know if it's the thing that, and then typically all these things are done, as I said, just in probability theory. Maybe there is no connection um, to entropy. And information entropy that I've seen in sort of classical spaces is typically everything is finite dimensional. Like even right now, there is somebody that sent me a link on somebody that does category theory with probability and derivation of entropy. But then, if I look at the space, at least my understanding it is just the space of simplexes, and the space of simplexes it's the space of finite. It's a space of a probability distribution of finitely many discrete elements, which is like even classical mechanics, that's not enough because you have you have the measures on phase space, so that already it's the space of measure is already infinite dimensional. So yeah, so we need to understand how to extend properly the information theory in the case of fields, and again, maybe somebody has already done it. I haven't like yeah, finding things in the literature is always hard, even when they exist. And then what is it? Evidence of absence. It's either absence of evidence is not evidence of absence. So the fact that I haven't found it doesn't mean that somebody didn't do it.
Mm-hmm. Okay. So how long is this next section? Can we
Yeah, in
finish
fact,
it?
let's see. It should be fairly short, but it's dense. Oh, but it's fairly short.
Okay.
Let's just do it then.
Okay.
This is so cute.
Okay. Classical uncertainty principle. Before concluding, let us turn again to the problem of zero measure on individual particle states. As we said, a distribution over phase space can be made arbitrarily narrow and in the limit of a delta function, the support will be a single point. Since the entropy is the logarithm of the phase space volume, which is 0 for a single state, the entropy of a delta function is minus infinity. Negative entropy is not compatible with the third law of thermodynamics, which states that the entropy must be non-negative. Therefore, on thermodynamics grounds, the spread of a distribution cannot be infinitesimal. This means that any distribution that is physically meaningful must have a finite spread in position and momentum. Conceptually, this sounds very close to the uncertainty principle of quantum mechanics, so it's worth looking at it more closely. First of all, since we saw that units have an important role, consider the expression for thermodynamic entropy S equals Boltzmann's constant times the logarithm of the number of states. Okay, volume of phase
you
explained.
later. Yes.
Okay. Given that a logarithm must take pure numbers, the expression is dimensionally incorrect. To correct it, we should take the equation where the volume is given in the units of something.
Yeah.
Okay, it's algorithm. Sorry. Where H can be understood as the volume for which the thermodynamic entropy is 0. Okay, then the footnote, we stress that H is defined purely from the 0 of the thermodynamic entropy, and it would be a value that is to be found experimentally. Experimentally, one would find the value of the Planck constant. As we saw, units of momentum are units of configurations of areas in phase space over units of position. Therefore, we can choose units of momentum such that H is numerically 1, but not dimensionally. To keep track of the value and units, let QP in brackets denote the unit of the product between position and momentum. And let W and H in parentheses denote the respective numerical values. We have the equation which tells us that entropy is.
So you take the entropy, so you have the logarithm of the ratio of the two. You expand it by saying this is the value and these are the units. The units simplify, so you have a pure value, which is the ratio of the pure value. And now this is the logarithm of a ratio, so it becomes the logarithm of one minus the logarithm of the other.
Okay, so this clearly shows that changing numerical value of H changes the 0 for the entropy, and therefore the value of H can be fixed by requiring that the entropy is 0 if W is equal to H.
Okay, if W is equal to H, these two simplify, and therefore S is equal to 0.
Yes.
So H, basically, the only thing that it does is sets what is the 0 of the entropy.
Okay. To make the Gibbs-Shannon entropy consistent with the previous definition, we must set what the entropy as the information as function of density.
Yeah.
Yes.
This minus can be the integral of rho logarithm of H rho. So you have to put the H here, such that this was an inverse volume. Now it's multiplied by a volume, and now this is a pure number. Now you can take the logarithm of the pure number. We're fixing units. So this is the thing that, you start physics, so you do all this dimensional analysis, and then at some point you stop doing it and you write all these equations that make no sense. And then if you put the constant in, like physics comes out, which is extremely funny. Anyway.
Yes. So if we take a uniform distribution rho U over a region U with volume W, we find that the expression is the same as in the case of entropy.
Yeah, you find the connection between the two, because the density over U is basically H over, it's basically the inverse of W, right? W is the volume, so the uniform distribution, the density is the inverse of W, so I have inverse of W here, inverse of W here, now restricted to U. And this is a constant, and this is a constant, so basically you just have the integral of the QdP of U, which is W. So W and W cancel out, and you just get the KB logarithm of W over H, which was the definition in terms of volumes.
Okay, and similarly, we find that this information entropy is again the difference.
Yeah, it's basically, so this is what we typically write in physics when we are sloppy, right? We just write rho log rho without caring of what units they are, right? And what happens is that this H is basically there to fix the zero. So, if you're only considering entropy differences, the fact that you forgot that H doesn't really matter. But if you actually wanted to look at things properly, you would have needed that as well.
Yes, I guess it is like maybe just concept of changing coordinates. So if we just rescale coordinates, with some linear, in some linear way, then we change the scales. But since here we are interested in logarithms, then this ends up being a difference of numbers, I don't know, of something, and then this scale becomes just some offset.
Yeah.
Yes. Okay. Yeah, I guess I'll leave this to the other reader.
Right, Ben.
All right, we are now ready to study the relationship between spreads in classical phase space and entropy. We want to find the distribution rho with zero entropy that minimizes the uncertainty. To do that, we set up a minimization problem using Lagrange multipliers. We want to minimize the product of the variances sigma q squared, sigma p squared, which is equivalent to the integral of q minus mu q all squared times rho dq dp times the integral of p minus mu p all squared times rho dq dp, where mu q and mu p are the mean position and momentum under two constraints. Rho integrates to 1, and its entropy is 0. So we have these requirements, right? So L is going to be equal to this long expression that I don't know you want me to read out.
Yeah, I can describe it. So this is cool because this is something that you can give an undergrad to do. So this is the function that you are minimizing. This is the product of the variances. And these are the two constraints. The first constraint is that the probability distribution integrates to 1. And the second one is that the entropy is equal to 0, because this is the entropy and this is... and now it's just pure calculation. So what you do here is, okay, the 0 goes away. And is that the only thing that I'm doing? Oh, the KB also doesn't matter because if this is a constraint, it's going to be 0 regardless of what KB is. And so we can take KB and put it inside the lambda 2 for convenience. And then you just do the variation equal to 0. So you have this is a product of two things. So you do first the variation of one and then the variation of the second. So you have here the only dependence is of rho is here. So it's this part here is this part, and this is the full integral that comes here as just a constant. Then this works in reverse. We're doing the variation of this, so we're doing the variation of rho, and then this sigma q is just this part put here. And here you're just doing the variation of rho, which is going to be 1. The variation of 1 is 0, is a constant. And here you're making the variation of rho log rho. So you do the variation of rho, which is 1, so you just have the logarithm. And on the other side, you take the variation of the logarithm, and therefore you have an 1 over rho, and that simplifies and goes away. And now what you have this, you know that this is 0 if and only if, for all variation, if and only if this is 0. So now that this has to be 0, you take the logarithm of rho, which is the only part that has a rho inside here, you put it on the other side, and everything else here are essentially constants. And then you exponentiate, and you just have that rho is equal 1 over h, the exponential of the constant, so this is a number. This is something that has a functional form of essentially q minus some number square over lambda 2, and this is a p minus some number square. And so we recognize these as the product of two independent Gaussians.
Okay. That's cool.
Yeah.
Yes, we recognize that the distribution is a product of two independent Gaussians. We can therefore use the standard expression and calculate the entropy, which must be 0. So we find that rho equals this term here. And so the I of rho we know equals 0. Right, we can just plug that in here. And then
And then the cool thing is that sigma q sigma p is h bar over e. So there is an h over 2 pi, and then you get you call that h over 2 pi h bar, and so on.
Yeah, where h bar is conveniently we can use this notation from quantum mechanics that h bar is equal to 2 pi. Yeah, so we found that any distribution rho of q comma p with non-negative entropy, i.e. which satisfies the third law of thermodynamics, satisfies the inequality sigma q sigma p is greater than or equal to h bar over e. This is e is Euler's constant, to be clear.
Yeah, it's Euler's constant, yes.
Yeah.
Not the electric charge.
Yes. Okay. Moreover, the inequality is saturated, i.e. becomes an equality for Gaussian distributions. Compare this with the Heisenberg uncertainty principle of quantum mechanics, which tells us that every state satisfies the inequality sigma q sigma p is greater than or equal to h bar over 2, which is saturated by Gaussian states. Given the parallel, we call equation 1.226 the classical uncertainty principle. Note that the classical uncertainty principle has a clear physical explanation, the third law of thermodynamics. Given that all quantum states have non-negative entropy, the same explanation can be taken for quantum mechanics as well. Note that since E, which is about 2.7, is larger than 2, the classical uncertainty principle has a slightly lower bound. The reason is that at a given entropy, the product sigma q sigma p is minimized when position and momentum are uncorrelated. Given that the uncorrelated Gaussians are also independent, this means that position and momentum are independent when an uncertainty is the lowest, and the joint distribution is the product of the marginal. This cannot happen in quantum mechanics since they're this is a typo, but since we cannot write
typo, yes.
Yeah, since we cannot write the joint distribution of position and momentum. Classical mechanics, then, can reach a lower uncertainty precisely because position and momentum of the same degree of freedom can be independent variables. This result, that's very cool. That's very neat. Yes. This result also tells us the problem with Maxwell's demon. In the setup, a gas is separated into two chambers with a door, and a demon that sees the exact position and momentum of all particles can open the door, letting a particle go only from one specific side to the other, decreasing the entropy of the system. But knowing the exact position of all particles corresponds to having access to a state of minus infinite entropy, which is forbidden by the third law. Naturally, if we have access to a source of minus infinite entropy, then we can always decrease the entropy of any system by a finite amount without violating the second law. Given that minus infinity minus a finite amount is equal to minus infinity, the entropy is technically not decreasing. Very, very true. All right, yes, this final result should really make it clear that the foundations of statistical mechanics and thermodynamics are not separate from the foundations of classical mechanics and quantum mechanics. In any theory, states are better understood as ensembles, and pure states should be understood as the most precise ensemble that can be prepared in the theory.
So Julius, going back to your question, that's the fundamental insight that we use then to construct the base theory. So the base theory is going to be a theory of ensembles, and then the pure states are recovered from playing in such a way. We can probably finish at this. Well, it's already 8. I mean, the summary just has uh, it just has this diagram. I mean, there's nothing much else. We should probably stop and open for questions if you guys have questions.
I have a question. I'm not sure how helpful it is as a question, but I understand why in thermodynamics you can't have an entropy that's negative because that would imply there being less than one microstate corresponding to some macro state that you have. Um, but in our case, when we talk about entropy, we're talking about like an information entropy, right? Like an I guess an information entropy of the section of the total state space that we're looking at or something like that, which is like a similar concept, but are we sure that that's actually like that third law still applies, I guess?
So the third law is on the thermodynamic entropy. Information entropy can do whatever it wants. And the difference in our case in physics between thermodynamics entropy and information entropy is that um, the the thermodynamic entropy is taking a distribution over states, not just variables. So you are taking the entropy with respect of the measure of phase space, of volumes of phase space. And that's the part that it's important that it's invariant. Now, if you just take variables, right, you can take any variables and that variable could have an uncertainty that it's shrank as low as you want, and you would have a negative entropy. So if you just consider the entropy of the marginal on position, right, you could stretch position as much as you want, even if you have zero entropy on the joint distribution, and you can do whatever you want. So the difference between, let's say, information entropy and thermodynamic entropy is that really the thermodynamic entropy is defined on states, and states have to be invariant.
Mm-hmm.
So that's why when I write I always call it Gibbs-Shannon entropy, because the Gibbs entropy has to be taken on the microstates, not on any variable that you want. And if you don't do that, your entropy is going to be wrong. Like that's wrong in the sense that it does not recover the thermodynamic entropy.
Mm-hmm.
Right. So now the link to thermodynamics is on that entropy. So you have to do it in the correct units, in the correct um, what's it called, variables essentially.
Okay. Yes, that makes sense, I think.
And the other thing that people kind of miss when you have just plain information entropy on a continuum is that the information entropy on a continuum is automatically relative, and it's relative to a unit of your variable. So if you imagine a uniform distribution over a unit of your variable, that's the entropy zero. Then if you have a uniform distribution over half your variable, then that's entropy minus 1, because you are giving more information than the unit, so it's a lower, right? And so on, right? That's so the essentially it's like the units already sets a scale for your zero for the entropy, and there is sort of a natural, let's say, scale when you have what's it called, when you have continuous variable information theory, in the sense that the noise floor tells you what the zero is. Like whenever you have information entropy, like the actual thing that you care is sort of the difference between your signal and the noise. And that tells you the maximum essentially bandwidth that you're going to be able to communicate. Like all of Shannon's theory was to create this theorem that tells you what is the maximum bandwidth that you can have. And then it took like, I don't know, 90 years for somebody to find an encoding that it's maximally efficient with respect to that. right? That was sort of Shannon's goal. It was not thermodynamic and so on. But the way that we can reinterpret all of this physically is that that zero of the entropy, the floor, is essentially background noise. Right? If you imagine that you are preparing a sample, right? Of course, you can't control everything in the universe, right? And in principle, if somebody on Mars is moving around, is making a gravitational wave, is going to interfere with your things. But you say, okay, but that's small, I'm going to disregard it. But you can imagine that by simple argument, there is always a floor, and you can't go below that floor, right? And so physically, you can imagine this third law as being basically telling you there is a uniform floor of a background, and you can't go below that. And there are different ways that you can justify that there is such a floor. It's kind of like all these bits and pieces we have to do the reverse physics of thermodynamics, but we haven't written them yet. But one way that you can say is that, for example, nothing can ever be fully isolated by everything else. So if you had a system and it would really be perfectly isolated, it means that every signal that you send just goes through the system and never touches the system, which means you can't even say that the system exists to begin with, right? So saying that something is absolutely perfectly isolated is basically saying, well, the thing does not exist. So you can't be perfectly isolated, therefore you must have some kind of interaction with everything else, and everything has to interact in some sense with everything else, therefore you have to have a floor of the noise. That's one way that you can justify it. Another way that you can justify it is say, look, if I told you that the system is not there, I gave you a complete specification of the system. So now, any other specification of the system, when it's there in terms of variables, cannot have more information than just saying the system is not there.
You didn't get a report. You didn't get the report.
One problem I would have with that is, let's think about the case of cosmology. Because if we assume that cosmology started with, uh, the empty set and produced the universe, then
The empty
clearly,
set is not a physical object. We don't measure empty set.
true, that's true.
So it's just I have a system. It can be in different configuration. One configuration is that the system is not there because I haven't prepared it, or the system is there and it is fully identified by these variables. Now, the point is that there has to be, like, if you have these variables that are on a continuum, and you can say, oh, but it can always be better and better and better specified, at some point there is going to be a system where you're going to have an entropy that is lower than the entropy of the system is not there state, of the null state. And that can possibly be in terms of this information description, because otherwise you would be saying that now I gave you a specification of the system that it's better specified than just saying the system is not there, which of course does not make any sense because the system is not there is already a full specification. So this is another way that you can justify the third law. But again, all of these parts are not already done in terms of the reverse physics of thermodynamics. So these are just sort of ideas which need to be tested. But okay, so if there
Sorry.
are any other questions on, yeah,
Maybe
Julius,
one
go
more. Yes.
Yeah.
Yeah. Just so to me, the very interesting part is this. How to say, derivation of classical uncertainty principle, whatever classical means here, because usually, like when we consider a classical system, like we usually we should be talking about a limit when the variables are rescaled. So then I would understand that in quantum case we have this limit. In the classical case, the bottom is so far below that we don't notice it, we don't feel it. But now we have this classical uncertainty. So the question is like, how should we take this limit? Like, is it even realizable? But if we take that the quantum is the more fundamental approach, then this classical limit is just, I don't know, it's just for comparison. It's not really like, cannot be achieved by an experiment.
Correct. So we actually, in all of this, we just finally paper got accepted on the quantum classical mechanics as a high entropy limit. And so the way that we understand the classical limit is not that I'm taking these uncertainty and make them small. Is that I have an entropy on the quantum states so high that if I can pretend that my states our distribution over things that are infinitely well defined, I'm not making such a big mistake. It's like my entropy is so high that it hides all the quantum effects, and then I might as well say that my state is an ensemble of a classical system, of a quantum system. So this is again why looking at saying that the classical system is an ensemble and not just point particle works a lot better, because then when we do the classical limit from quantum mechanics, we recover those ensembles that can be seen as made of infinitesimal parts, but the infinitesimal parts are never there. You never recover the infinitesimal parts.
Yeah, indeed. And another question is more about curiosity. So whenever we see these numerical constants appearing, it's always a question. Let's say when we see 2 pi, the question would be like, where is the circle? And the circle probably comes from Fourier transform and stuff. So similar question is, where does the E come from? Where's the compound interest here? Or maybe so.
Yeah, and that basically comes out from the Gaussian. Like the Gaussian has both the E and has the 2 pi. That's let me get back because I was also wondering that, and somehow this also tells you that, which is kind of the kicker. So when when you calculate, there you go, the entropy, right? The entropy is going to be the product of the uncertainty divided by h times this 2 pi e. So if you had a uniform distribution, you wouldn't have that 2 pi e. That's exactly what when you do the Gaussian, you get this 2 pi e, and now since you know that this has to be equal to 1, you get this 2 pi and the e. And there is, if you're wondering why the Gaussian distribution has a pi, there is a wonderful video from 3Blue, 1Brown that shows you that, and it's because of the symmetries of the Gaussian. And the E comes again from the fact that you have something that it's in a sense recursive in the Gaussian as well, so that you get your compound interest.
Yeah, that is
Yeah.
always funny to understand the origin of this.
Yeah, and the other thing is also like these type of things also tells me like there is a sort of a perspective where they try to say like in math, right, that there are the sort of the constructionist people that don't like real numbers and they say, oh, we should have everything finite because everything is finite, right? But again, in physics, at the end of the day, we use models, and these things sort of appear so simply with making very simple assumptions that these are kind of the reason why I'm perfectly okay with real numbers and these limits, even though we we know that they don't exist in the same way that we know that the point particles do not exist, right? We know that ensembles as infinite collections of preparation also cannot possibly exist because we're never going to make them. But there is this sense that in physics these are our theoretical objects. And again, it's so funny because we model reality with things that are highly idealized that we know that they can't possibly exist, but they're very productive. So. Okay, so we are 15 minutes after. If there are no other questions directly on these topics, we will have also to understand what we want to do with the reading group. I mean, there is the whole part of physical mathematics, but it's gonna change completely the tone, which, I mean, there are people that are more interested in the math that might be more interested in that anyway. We can continue with that, or if we can also repurpose it to talk about other things. We should just talk on the Discord server and decide. Okay, so let's stop. Thank you for everybody who is watching us from the internet, and see you next week. Bye.
Bye-bye.
Bye.